The game of Nim is a really simple one. You have a pile of matchsticks on the table. There are two players who take turns and remove 1, 2, or 3 matchstick in each turn. The one to take the last matchstick loses. There are many variants of this game, but this is the one we're going to do now. And let's see if I can beat the computer. There are 15 sticks left in the pile. I'm gonna take 2. And then the computer will take 3, I take 1, and then I take 1 again. Oh, there are only 2 sticks left, so I'm gonna take 1. Therefore, the computer had to take the last one, and the computer loses. A round of applause for me for winning. If I have made a mistake, then I would have lost. Let me show you why. So let's write the game of Nim once more. I'm gonna name this Nim game 2.py. Okay, here we go. The first thing that we need is just the number of matchsticks on the pile. So I'm gonna call that pile size. 10 is fine for now, okay? And then we're going to learn a new control structure, which is the while structure. The while structure requires a logical statement, a condition, and as long as that condition is true, it keeps repeating the indented block again and again. And here, obviously, we're going to play the game as long as there are any matchsticks on the table. That is, while the pile size is greater than 0. Okay. I will accept the suggestion of the AI, which is not good, but it's a good starting point. So we do print that there are pile-size sticks left in the pile. In case I haven't mentioned, or maybe you forgot, the F string is a special formatted string. When you put an F before the quotation mark that marks the beginning of the string, you can use variables inside that string between curly brackets. Actually, you could have any expression here, any Python expression. It gets evaluated and put into the string, so that's a fairly common and very comfortable way of putting variables into your strings. And then we are going to input the number of sticks, and since the input will return a string, we will convert it to an integer. If the user makes a mistake and enters something that is not a number, we will just get an exception and the code stops. That's fine for now, we're happy. And then we just remove the pile, reduce the pile size with the number of sticks that the player removed, right? This notation is actually just an abbreviation. This is exactly what it means. Pile size equals pile size minus player move. The way I usually read this is let pile size equal pile size minus player move. But this way you type pile size twice. Oh my god, this is quite a language breaker, pile size twice. You do that, so instead of that we just abbreviate like this. It's the exact same thing, it's just easier. Okay, this is a very simple one, and what it does is it makes two fictional players play. So let's test how this works. The first, there are 10 sticks left, so the first one takes 3. Okay, there are 7 left, the second one takes 2. Now I have to remember that is the first one again, so it's kind of lame. That takes 2 as well, and then it takes 3, and whatever happens, the last player lost. But we don't know who it was because, yeah. Here's the thing, this is not very good, so let's improve on it. Okay, so we want to play against the computer. So the next thing that I'm going to do is, first of all, immediately after reducing the pile size, I need to check if the player actually took the last stick. Because if they did, I definitely have to print that the player is dead. So if pile size is less than 0, that's amazing. And then I say, you have taken the last stick, you lose, which is perfectly correct. And then I do something interesting, which is called break. So the break jumps out of the current loop. Okay, so we are now in a while loop. That's the indented block that we are in. So break will move out to the exact same line. You see that there are these thin lines here, but the point is it's the indentation. You can see that the break will jump out right here, yeah? Instead of this, I will just say game over. I think this is enough. for now, okay? So that's what break does. It jumps out of the whole thing. And now the computer move suggests to do a random pick. We have not discussed this, so let me describe what this does. Import random, okay? Random is a module that we can import, and it has many functions that all revolve around generating something randomly. And this one, as the name suggests, generates an integer randomly between the numbers given, so 1 and 3. It's something we call a closed interval, meaning both 1, 2, and 3 are possible values, okay? That is important to remember because some other randoms do not include the closing part, but the integer one does, so this is how it works. Okay, so this generates a random number which can be 1, 2, or 3, and then the computer takes that many sticks. The same way we reduct the size of the pile with that number, and if it's out of piles, then we say the computer has taken the last stick, so you win. Okay, still nothing particularly complicated. I think it's fairly straightforward code. You can almost read it in English. The only exception is the random part that we have not discussed before. Okay, let's go. Okay, so there are 10 sticks. I'm going to take 1, and the computer takes 2. I'm going to take 2 as well. The computer takes 1, so now there are 4 sticks left. I'm going to take 3, and thus the computer loses because there are only 1 sticks left in the table. Please note that the computer has taken 2 sticks, which is impossible. We're going to have to fix that in the next round, so that the computer only takes as many as there is on the table, actually. So this situation here, where the computer takes 2 sticks even though there's only 1 stick left, this is a typical example of a bug. And we all know what bugs are. We all have this intuitive feeling about them. It's that they are small errors that don't actually stop the program, but make it behave erroneously and kind of annoying things. But why are they called bugs? Well, guess what? In the first days of computing as such, where the presence of numbers was actually electricity flowing in the wire or not flowing in the wire, the wires were switched by relays, like physical connecting relays, to make electricity flow or not flow. And there was this addition error in 1947, so that was a very long time ago. This addition error that was caused by a moth being basically slapped to death by one of the relays switching on, but the dead body of the moth stuck there and didn't allow the relay to close, and therefore there was no electricity flowing even when the relay was closed. And this was the first computer bug. It was literally a bug, and that's why ever since we call these small problems computer bugs, okay? Just as out of for curiosity, yeah? Let me fix this bug, and the way I'm going to fix this is I'm going to use the minimum function, which is just called min, and of course we are going to use 3 or the pile size, which means, oops, that's not what I meant, min pile size or random number. Yeah, there you go. So if the pile size is smaller than the random number that we generated, then it will be picked. If the random number is smaller, then that will be picked. And this guarantees that we cannot ever have more than the actual pile size. Okay, so the bug is fixed, and we have learned a new function, which is the min one, that gets, in this case, it gets 2 inputs and drops down the smaller one of the 2 on the bottom. If they are equal, of course, it doesn't matter at all. That's how min works. Okay, so now we fixed that bug. However, this is quite a simple game. Let me do one more thing though. Now that we have learned the random integer function, let me make the pile size random as well, okay? So that makes the game a little bit interesting. And now, what I'm gonna do is 19 sticks left in the pile. Let me take 2, okay? And then let me take 2 again, and then I will take 3, and I will take 1 again, and I have 1. Okay, brilliant. So the next thing we're going to do, this works pretty fine now, so we can play. And what did I do here? How did I beat the computer? And I can beat it many times over and over again. Here is the thing that we need to think through. How can we win the game? By having the last moment of the game when the computer has only one stick in front of it to pick, right? Because then it has to pick the last one, and we have one. How can we achieve that? Well, if in our turn we have 2, 3, or 4 sticks. Because if we have 2, we take 1, so the computer is left with 1. If we have 3, we take 2. If we have 4, we take 3. In either cases, the computer is left with only 1 stick. Okay, brilliant. How can we get to that point? Well, if the computer has 5 sticks before our move, then no matter how much it takes, 1, 2, or 3, we will have 2, 3, or 4 sticks remaining. So we should have a position where the computer has 5 sticks before our move, and that keeps on going. So we can see that there's a formula here, which is 4x plus 1, where x is the number of steps before the end of the game. So in step 0, which is the last step, we need 4 times 0, which is 0 plus 1 stick for the computer. In step 1, which is the computer's move before that, we need x is 1, so 4 times 1 is 4, plus 1 is 5. We need to have 5 sticks on the table. The step before that, we need 9 sticks, and so on. You always add 4 to this, right? So the point is, whoever gets to make a move when there are 4x plus 1 sticks on the table gets to win the game. And whoever begins first has 2 options. Either there are 4x plus 1 sticks on the table, and then they have lost, whoever began, or they have more or less, doesn't really matter, and then they can take away as many to make it 4x plus 1, and then the other player has lost, okay? That's the way that it works. So now let's create a version of this game where the computer doesn't just make random moves, but is aware of the winning strategy and therefore always beats the player, okay? I'm gonna do that. So here, the player has made its move, yeah? Whatever it did. And now we need to check if we even have a chance. How do we check that? The AI is already helping. The AI knows the answer because, like I said before, I have already written this code and forgot to record audio, but never mind. The point is, how do we know if a number is matching the 4x plus 1 format? Well, we divide it by 4 with remainder, and if the remainder is 1, then it's obviously matching. This is called modulus. And if the modulus of the number divided by 4 is 1, that means the remainder, then that's a number in that format. So let me go ahead and do that. If the pile size time modulus 4 equals 1, that means we have lost, okay? We can't make a winning move. So we just keep on doing what we did before. I want to get the control back. This is the case when the computer takes control away from you, yeah? Here we go. And now, now it's the other case. And in this case, we are going to have to make a move that will make us set up for victory. Basically, that will make us go to the last, to the next critical point where our opponent, the player, has to take a stick when it's 4x plus 1 format. How do we do that? Yep, the AI is already helping. Well, we can take the number of sticks that the player removed and make it up to 4, because that's the idea. Once we get to the winning point, we always make sure that there are 4 sticks removed in each step. And then we will end up with the other player having 1 stick. How do we ensure that? We take the number that the player removed and make it up to 4. So if the player removed 1, then we remove 3, and so on and so forth. That's 4 minus the player move. I think I over-explained this one, sorry. I tend to over-explain stuff, yeah? And so now it will have, actually this is still not good. We have the same bug here, yeah? We need to have the minimum of the random and the pile size, of course, yeah. So we don't take out more than actually is there. Let's not make the same bug twice, right? Okay, that is it. So now we have a computer algorithm that always wins the game. Let's see if this is the case. Now we have 17 sticks, and the funny thing is 17 sticks is 4x plus 1 if x is 4. So we are 4 steps behind losing, and yeah, that's too bad for us. We have lost because now I'm going to take 3, doesn't matter. And you can see that the computer is following the 4x plus 1 pattern because 13 is also 4x plus 1. So I'm going to take 3 just so we finish faster. And now there are 5 sticks, which we have discussed as a losing position. I'm going to take 3, and then of course the computer takes 1, and I have to take the last one, and I lost. Okay, bad luck for me, computer won. Okay, there are 14 sticks. Aha, now is my chance to shine because 14 is not 4x plus 1. If you divide 14 by 4, you get 2 as a reminder. So now I can make it to 4x plus 1, 13 by taking 1 stick. And you can see that the computer took 2 sticks, which is clearly not 4 minus 1. It was the random case kicking in. Now the computer knows that it has no chance. And now I'm going to employ the same strategy, meaning 4 minus the number of sticks the computer took, which is 2 sticks. I will take 2, computer takes 2 again. I will take 1, and ta-da, the computer has lost. A round of applause for me for winning the game. There we go. So that's the winning strategy that you can follow in the game of Nim. Let me play one more just to see if it still works. 10 sticks, that's again, reminder of 2. So I'm going to take 1 to make it 4x plus 1 format where x equals 2. And the computer takes 3, so I'm going to take 1. Computer takes 1, so I'm going to take 3. And boom, I have won again. Mathematics works. That's amazing. That is absolutely brilliant. So now there is only one issue left, which is the player move. We never verify how much sticks the player takes. So what we can technically do is in the first step, take 18 sticks, and then the computer has to take the last one, and we have won, which is of course cheating, but it works because we never check that. And there is a way to check it. I'm going to show you 2 ways to check this. The first one is like this. If player move is less than 1 or greater than 3, then we print that this is not a valid player move, and then use the word continue. Now, break was here, and break meant stop doing this loop that you're doing now and jump to the end of it. Continue means stop doing the current loop and jump to the beginning of it, meaning don't continue evaluating the current loop, but start over again with the next one. And here, this has an unpleasant side effect, which is we have already printed how many matchsticks there are left in the pile. But if this happens, we jump back to the beginning of the loop. Therefore, we print it again and again and again. This might not be necessary. So what we're going to do instead is take a different approach, use something we call a nested loop. So this while loop here repeats everything that is indented, so like this part. And now inside that loop, we are going to create another loop. Why not, right? There is nothing against that. So I'm going to say while player move is less than 1 or greater than 3. But in the very beginning, now I have this question twice, okay? Bear with me because this is something that is a very programmatic thinking. And if you kind of catch up on this mindset, then you might be made to be a programmer. So the thing is, this one is repeated twice, which is not something we like. Right now, it's not a big deal. It's just a message and just converting to the integer. It's okay. However, here we could have an arbitrarily complex operation that we would definitely not want to have twice. So here is what I'm going to do instead. Instead of repeating the code, I'm going to make it artificially wrong. I'm going to give it a value that is absolutely not okay. And therefore, I'm going to force the loop to kick in, right? With this movement that I am making the player move illegal, it definitely will have to enter the loop at least once. And then all I need to do is remove this, because now, even without the player entering anything, we do have this player move verification, and I will have to do an if here, right? Okay, so let's try to read out what this does. It's really important that you understand this. We make player move 4, which we know is wrong. And while the player move is wrong, and actually here we get a hint from the AI, but we'll get back to that in a second. While the player move is wrong, we are going to ask it whether what the next move should be, right? Regardless of whether the player, sorry, this loop is executed at least once because I made it arbitrarily wrong. If here the player enters a right value, we jump this one over, we never go into this block, get back here, see that the condition is now fulfilled and continue with our lives. If not, we are going to print this, this actual warning, okay? Let me show you how that works. So now I'm going to take 0. That I cannot do. Please enter a number between 1 and 3. I'm going to take 4. No, that is not a valid move. I definitely have to do, 3. I was not paying attention. I'm going to lose. I'm going to lose. No, I'm going to win. Haha, I won. Yay, brilliant. I wasn't even paying attention, but I still won. Brilliant. Okay, and there's one more bug left, which is if the pile doesn't contain as many sticks as we need now, we actually still accept that. So we're going to do this like this. Yeah, thank you. So what happens is we're going to check if the player's move is valid in the first place, and then we're going to check if there are enough sticks in the pile in the first place for the player to make that move. Now I also have some repetition here, which is the condition. Yeah, I am having the condition twice, and it's not even a very trivial condition that I have to live with. So unfortunately, I can't have the best of both worlds. I would either have to duplicate the input line or have to duplicate the condition. But the thing is that if this was proper programming and not just me showing you some interesting stuff, this is what I would do. I would go ahead and say if player move is less than 1. And then I would say invalid move. Your number is less than 1. Yeah, I would say your number is less than 1. Yeah. As if it's greater than 3, I would say print invalid move. Your number is greater than 3. As if takes more than the player, then I would say print. Oh my God, I'm losing control of the invalid move. You're not. There you go. And now I don't need this, right? So that's what actually typically happens in these cases, is that you have one big condition that evaluates everything, but in order to give a better error message, you actually break it down into different cases. And look, if somebody doesn't know the rules of the game, they will be super confused, or they could be super confused if they say 0, I don't want to take any. And then it says, the problem is that your number is less than 1. Then I want to take 4. Your number is greater than 3. So now it's much more human-friendly, so to speak, okay? Am I going to lose now? No, I'm going to win. 3, oh no, I'm going to lose. I did. I have taken the last stick. I was not paying attention to that. Okay, now we're going to do a class-based implementation of the same thing, just so we practice the creation and the instantiation of objects and classes, okay? I'm not going to remove this. I'm just going to create a class Nim game, okay? And as we have discussed, I am losing control of cursor again, but we always begin with an init function actually, and yeah, pile size is really a good idea. For now, all we are going to do is save the pile size into ourselves, so that's perfectly fine. That's how we initialize this game, okay? And then we are going to create a getPlayerMove function, okay? I'm going to learn to put the column in the right place. And yeah, it knows already that what we have on mind, so that's pretty much a good thing. We are going to use the same strategy here, so make a deliberately wrong value hard-coded, and then while the value is wrong, we ask the same question again. Okay, and then we just return the player move. So this function does nothing else, just gets the player move, okay? And then we are going to have computer move, very obviously. And the AI will probably help with that as well. So computer move is either random or the winning move. That's exactly what it's going to do, right? So the important part here is that I am decomposing the entirety of the game into smaller pieces that can be made into class functions, and they still make perfect sense. So watch how easy it will be to have the play function, which takes as long as there are sticks in the pile, of course. And then we get the player move. We deduct that from the pile size, check if the user has won or lost in this case, and then we get the computer move. Actually, this could be even made into a proper function. Let me make that into an even more, because if you have a look just by eyes without understanding anything, this looks extremely similar to this, except for the fact that the variable names are a little bit different. And that's kind of a surefire way of telling that probably they could be made into a def make move self and the participant, who can be, of course, a player or the computer. Nope, I don't like this. Let me do it like this and num removed, yeah? Num removed. And then we don't care who it is. All we do is self.pile size is less than the num removed. And then we say if we ran out of sticks, right? Then we print whoever has taken the last stick, so the other participant wins, right? It's loses. It's not wins, it's loses. The AI got it wrong. Of course, that also is an option to play this game, that the one taking the last stick wins. And then the math is a little bit different, but it's basically the same. Not that much different. What is get computer move? Oh, I am having an underscore here. Oh, self.player move. Ah, yes, this is interesting. So let's see what the problems are, because they will be pretty self-explanatory. So here's the thing. How can we make sure that the computer knows what the player did? The only way to make that sure is to save it in a variable, which is exactly what we did down here. We had the player move variable, but now we are in a class instance, so all we can do is save it as a class variable. But in order to save it as a class variable, we need to create that by initializing it to 0. Interestingly enough, we don't need the computer move because we are absolutely not going to use that, right? And that's exactly the way that we are doing this. It's half fixed, half not fixed, so bear with the AI for a moment while it fixes everything. Yep, now it did. So now what happens is we are doing the exact same thing as we did before, but instead of using a variable in the function, we are using an instance variable. So a variable that is inside the instance. And that is actually important, because this way, when the computer needs to make a move, it can actually use the player moves to calculate what it needs to be done, right? And then make move says we reduce the number of the size of the pile, and whoever took the last one loses, the other one wins. Excellent. And now we can do the play function, which look what it is. It's like 4 lines literally. It's 4 lines. If I'm giving a game over message, then it's 5. While there are sticks in the pile, we get the player's move, right? And then we make that move in the name of the player. And then we get the computer move, and we make that move in the name of the computer. But making a move is actually just one function, regardless of who does it, which is fair, isn't it? Because both the player and the computer should have the same chances. And then we print game over, and that's the way that it works. Okay, now let's see how this works. Very simple. We instantiate this class with a random number between 10 and 20, as we did before. That's going to be our pile size. And then we just call the play function, which is a loop until we run out of matchsticks. we should see basically no difference whatsoever. The question is, how many sticks do you want to take? But I don't know how much we have. Oops, we do see some difference. Get player moves should clearly say how many we have. Oh, we say that right here. Print. Yeah, there are that many sticks left in the pile. Note that we are using the instance variable here, okay? So now I'm going to say there are 17 sticks. Oh my God, we have lost. Doesn't matter. I'm just going to go ahead and take 3. And boom, I made a bug. Yes, this is absolutely great. And the reason we are not editing this out is because everybody makes bugs, and when you are making any kind of refactoring or transformation on your code, it is perfectly natural to make mistakes, and then you're gonna have to find them. And this is a great opportunity for us to analyze what happened here. We know that we have called the function in line 44, which is how the whole thing begins, right? It's the entry point of the whole game. And then we know that the next thing we do is the make move, which calls the computer move. However, we don't have self.computerMove. This was a mistake that was introduced by the AI, whichever AI it was, whether it's Copilot or Claude Sonnet, we never know. But the point is, we deliberately never created a variable for the computer move, right? So of course, when we try to call it in line 40, we ran into a problem because we don't have self.computerMove. But there is a suggestion, did you mean getComputerMove, which is the actual right answer. And it is also underlined, so it's my fault. If I would have taken a look at the problems, it clearly states here that the instance of Nim game has no ComputerMove member, right? The very clear message, the instance of this class never created a ComputerMove, so it doesn't have one. Perfectly true. The way to fix it is, of course, exactly what it suggested. We need getComputerMove, right? And watch what I did here, in case you're not familiar with Python as much. I called a function which required 0 input from me. It requires self, but self is here, as we have discussed previously. And whatever fell out of that function, I immediately use it as the input of the next function, right? I could, of course, go ahead and say ComputerMove is self getComputerMove and then pass that variable. But why would I use another variable when I actually don't need it? I'm never going to use it again. So I can just go ahead and boom, do it like this, okay? And now this will work. Don't believe me, don't ever believe me. There could be other bugs in here. Let's run it and see. Okay, 4x plus 1 is what, 13? So I'm going to take 1 stick. Okay, and I never found out how many sticks the computer took, which is another bug. But I know that it was 3, so I'm going to take 1 again, 1 again, and 1 again. And so computer loses. A round of applause for me. It never said I won, but the computer lost, so I had to win, right? So of course, not seeing what the computer did is not okay. So what we're going to do is, wow, look, I have forgotten this here. This doesn't make any sense. You should have let me know. But of course, I'm gonna do computer move equals self.getComputerMove. Of course, then we are going to make that move, computer move. And there is one more thing that I can do here, which is, actually I'm not gonna, where should I do this? And that's exactly what programmers do in about 25% of their times. Where should I put this? I am willing to print the number of matchsticks that a computer is gonna take away. Should I be doing this in the getComputerMove one or here? Or maybe in makeMove one? Yeah, I think makeMove one is the best. Make move is the best because that's, again, uniform to everybody. So it's a nice touch. Okay, there you go. And then participant takes num remove sticks. Let me go ahead and shrink down the code here, because now get player move actually puts the player move into a variable that I'm actually using. Oh wait, this is a good touch. If self pi size is less than 0, then we don't need a computer move anymore. So yeah, this is unnecessary because when we reach this point, the next thing we're going to do is check if the pi size is 0 anyway. So yeah, it's fine. Okay. Leave me alone, please. Okay, and leave me alone, please. Thank you. And so the philosophical question is, because get player move does return the number. So I can go ahead and shrink my code a little bit down and go ahead and do this. Let me shrink it down a little bit. Watch this, what I'm doing. I'm not going to use the variable. I consider that to be a side effect. And I don't need a variable here anymore either. Yeah, there you go. So now it's only basically 2 lines, except for the verification. Yeah. I could actually shrink it down even more, but it's fine. I think readability is the single most important thing. I don't care if your code is optimal or fast or Pythonic or elegant. Screw all that. You're not gonna benefit as much from them as a readable code, because what happens with your source code, I don't care who you are and what you do for a living. What happens to your source code is you're gonna put it on a shelf and forget about it for 6 months. And then you're going to come back and you badly need that code and you badly need to make it work again, and you will not remember ever writing it, because that's what happens to all the source codes. And then there is a time that you require to reload the whole thing into your brain and make it work again. The shorter this time is, the better. That's the only thing you need to optimize for, because when you need that code again, that time will be very expensive. So all you need to make your code to be is readable. You look at it and you're like, oh yeah, make move, yeah, that makes sense. That's what takes a number of sticks away from the pie. Yeah. And then play, yes, I see it's the loop. Yeah, that's the one that makes the moves. That's the only thing. Really, really important. Trust me on this one. If you don't believe anything else to me, just believe this one. Make your code readable is superior to everything else. Okay, let's see if I introduced any new bugs or this actually works now. Okay, 14 sticks left in the pile, so I'm gonna take, how much? 1, yeah, there you go. Player takes 1 sticks, computer takes 3 sticks, so there are 10 sticks left. Since the computer took 3, I have to take 1. Computer takes 3 again, I'm gonna take 1, and there are 2 sticks left, so I'm gonna take 1, and computer loses. A round of applause for myself. Excellent. Let me try to make some illegal moves. I'm gonna take 13 sticks, so the computer is only left with 1. Of course, not gonna be able, my number is greater than 3. Okay, brilliant. Then I'm gonna take -5. That's less than 1, so yeah. 14, so I'm gonna take 2, and then I'm just gonna have to look at what the computer takes. Oh, I was not paying attention, sorry. That's not true. I would have been mindful, should have been mindful in the last step to only take 1, but yeah, okay. I lost because I wasn't paying attention. Guys, that's the code. That's where we're going to end this little adventure of Nim game. This, I think, is pretty much as good as it should ever be for such a simple thing. If you are a little bit more in the routine of implementing stuff, very likely you will begin with a class-based implementation, because like in this case specifically, we could have a simultaneous game of Nim, like how many Nim games can you play at once? And well, it's a pretty high number because it's very basic. As you can see, the maths, it's very easy to play 100 games at the same time and still win all of them, unless you get unlucky, but then you will not win them anyway. So yeah, that's the game of Nim that we're playing. Thank you very much for watching. I hope you liked it and took some value out of it. I will definitely looking forward to see you in the next one. Bye.